evidences which are supporting the generation of hot and dense matter at high energy heavy ion collisions. And one of them is the elliptic and triangular flow, which we could get from two particle azimuthal anisotropic correlations. The second order of the free cosine coefficients, we call it the elliptic flow component, while the third order of it is the triangular component. Our physics value, V2 and V3, are actually the square root of the second and third order of the cosine coefficients. And they are assumed to be the strong evidences of the hydrodynamical equilibrium is occurring. So these results are also assumed to be the evidence of the pre-equilibrium effects are propagates to the final stages. And about the small collision systems, there are many observations which supporting the tiny hydrodynamical equilibrium stages. The left figure here is the 2D temperature profile calculations from SONIC, and this shows the head-on collisions of the P gold and D gold and helium-3 gold collisions. As you can see from the most left panels, the temperatures looks enough to generation of the QGP. And from the most right-hand side panel, the P gold is the circular dominant flow component, while the D gold and helium-3 gold are elliptical and triangular component is dominance. And the right-hand side figure here is showing you that about the centricity calculations from the MC Glauber model. The red data, which is the P gold, shows the smallest second order of the centricity, while the D gold and helium-3 gold look similar to each other. And about the third order of the centricity, the black data, which is the helium-3 gold, has largest, while the P gold and D gold looks kind of small. And actually, this measurements of the data gave us the similarity of the hydrodynamical estimations. So for the V2 case, as a function of the PT, the size of the P gold data is smallest, while the D gold and helium-3 gold can have the similar size of the V2. And likewise, for the V3 case, the size of the helium-3 gold is the largest among these three small collision systems, like we can see from the eccentricity calculations. And this confirms of the initial geometry effects are propagated to the final stages, as we seen from the heavy ion collision cases. Also, it is giving you that the information that the hydrodynamical calculation has a good estimations to the measured data. So because of the I'm the first speaker from Phoenix Collaboration, let me give you some brief overview of the detector informations. Left-hand side figure is the Phoenix BeamView detector figure system, Phoenix system from the BeamView. The green area we call the CNT systems has the capability to measure charged particles and the PIDs. And the right-hand side figure is the Phoenix side view systems, and they can measure the charged particles and also gives the trigger and event plane informations. For the small collision systems flow analysis, we use the CNT system here and the FATX here and BBC. So we can use the we can calculate the V2 as a function of the PT at the CNT and also V2 as a function of the pseudo rapidities. This diagram, which you can see at the top corner here, shows you that the pseudo rapidity coverages of each detectors which we are using. So the Phoenix central arm, which we call CNT, is covering the mid rapidity ranges, and FATX and BBC is actually covering the south and north backward and forward rapidity areas. And because of their system, even if the same detector, which we call the FATX, the south and north arm is actually the independent subsystems. So basically, we can use the five independent subsystems to calculate the V2. Okay, so before I actually move on to the introduce you that the latest Phoenix analysis results, let me give you some brief item that I want to claim in this talk. So when the free expansion works for flow, so this simple equation here should have to be works, and this is what we call the flow factorizations. This here A and B is supposed to be the independent subsystems of it. And this is actually based on the idea that the medium particles should correlate it to each other, while the non-flow particles are uncorrelated with the flow medium originated particles. And at the larger multiplicity events, that the medium particles are supposed to be dominated so that the signal part so that the influences from the diejet or jet particles supposed to be successfully suppressed. And this is the V2 calculations from the CNT area, which is the mean rapidities. And this method is which we call the 3x2 particle correlations. To do this, as you can see here, we need three independent subsystems for calculation of the correlations. This combination here that I show you right now is the actually usual calculations, kinematic selections for the calculations from the Phoenix V2 measurements. And because of we are selecting two backward systems, as you can see here, BBC South and WDX South, the reason why is that we using the asymmetric runs so that the higher multiplicity are accumulated at the south sum. So we are usually using the this kinematic selections to accumulating some larger multiplicities. And this kinematic selection is actually used to calculate the Phoenix nature results, published results. So I'm going to call it from it because of we are selecting two backward systems. So I'm going to call it the Phoenix BB calculations. And new kinematic selections, which is the one forward rapidity this year, forward rapidity detector is included, is to used to the study the flow factorizations at the small collision systems. So I'm going to call it the Phoenix FB calculations because it has one forward and one backward. One is from the backward. So when you trying to calculate the V2 with flow factorization, when the flow factorization works, then when you're trying to get the V2 SCNT, then these two calculations of the 3x2 particle correlation is supposed to be giving you the identical value within the statistical or systematical uncertainties. However, we found there is a difference between these two kinematic selections. This result was actually presented at the Koch-Meter 2019. As you can see here, the Phoenix BB calculation has a smaller value of the V2 at the at the same mean rapidity ranges at the same physics value, which is the V2. And Phoenix FB results, which has a little bit larger value, and this difference is actually cannot explained by the within the uncertainty ranges. Since the nature results actually published by the event plane method with Phoenix BB combinations, and you can see that they are actually explained perfectly so that we can confirm that this difference between two V2s are purely from the kinematic selections which we are using right now. And this is first this is because of the first the correlations effects from the Phoenix FB results, because the larger pseudo rapidity gap is accumulated at the denominator, so that the correlations between the VT south north has the large pseudo-rapidities, so that the correlations, strongness of the correlations are kind of suppressed. On the other hand, at the same time, the small pseudo-rapidity gap at the denominator from the Phoenix denominator, Phoenix BB calculations are actually giving you that the small size of the V2 because of they are located at the denominator, as you can see in the previous pages calculations here. More for the more sophistications of these interpretations, we are having the latest publications from the Phoenix, and this is already on the archive of these results. So let's say the most left-hand side figure is the V2 with the P gold 0 to 5% centrality, which is very head-on collisions. The middle one is about the D gold, and the most right-hand side figure here is the helium-3 gold results. And the BB calculation, which is the previous Phoenix usual kinematic selections, are giving you that the perfectly reproducing the Phoenix event plane calculations, which was published in the Nature Physics. And this is actually confirms that the Phoenix nature results were Phoenix nature results with the same kinematic selections. And also, this one is showing you that the Phoenix FB combinations, which gives the explanations of the star preliminary results of as like the previous page, this most left-hand side figure is the V2 at P gold, 0 to 5% centrality, and D gold, and the helium-3 gold. You could see that the larger V2 compared to the Phoenix published results at all of the three of the head-on collisions cases. And because of the V2 from different kinematic selections, it gives the different size of the V2 in all three of the collisions. And we can claim that the flow factorizations at the small collision system is actually broken in here. But if you see more concentrated on this, then you can see that the higher multiplicity events looks more recovering the flow factorizations more than the smaller collision systems like P gold. And this figure here is the Phoenix V3 calculations as a function of PT. Like the previous case, the Phoenix BB kinematic selections of the 3x2 particle correlations gives the perfect description of the Phoenix Nature Physics publications, like with the same kinematic selections. So this most left-hand side figure is the D gold V3 as a function of PT, and the right-hand side figure is the helium-3 gold. So you can see that nature results from the Phoenix is also V3 are also confirmed perfectly. And this result is actually calculation from the FB combination, which is including 1,4 rapidity. And this open area, you can see that it cannot reproduce neither star preliminary non-physics publication results. So that here now we can see that using the FB combination is actually giving you that the imaginary size of the V2 at P gold and D gold, while the V3 at helium-3 gold is actually explained by the FB combinations too. Which means that it seems like the stronger no-flow effects at denominator or event plane decorrelations effects is working at the numerator, so that it can be caused the imaginary size of the V3 at the smaller collision systems like P gold and D gold. And as you can see here, that the differences between two V2s are actually suppressed by the helium-3 gold multiplicities. which means that the helium-3 gold cases, it seems like the flow factorization is kind of recovered. And this brings us to here my summary. So published results calculated by event flame method are actually confirmed by the same kinematic selections of the 3/2 particle correlations of the V2 as small collision systems. And kinematic selections are, as you can see, the kinematic selections are very important to understand the flow, especially at the small collision systems, because of the small multiplicity cannot suppress the non-flow effect perfectly. And now Phoenix has an analysis effort in explaining and quantitating the differences between these kinematic selections right now. So this is my summary. So thanks for your attention.
Thank you, Professor Han. Any questions? Okay, we have no questions. Then let's come to our next speaker, Vladislav Borisov, St. Petersburg Polytech University.
Hello, can you hear me?
Yes.
Okay, I share my screen.
Okay. Go ahead.
Can you see my slide?
Yes.
Okay, I will start. Hello, everyone. I'm Vlad Borisov from Peter the Great, St. Petersburg Polytechnic University. And today I would like to tell about exploring hadron spectra in small collision systems at Phoenix. Sorry. We will start with discussing importance of strange and hidden strange particles. Then I will present ratio of Kn to pion and proton to pion in small system collisions. Then I will present nuclear modification factors of charge Kns, K star, and 5 mesons in plenty small collision systems, and compare them to non-strange hadrons. And then I am going to summarize my talk. Comparing production of particles with strangest content to the production of hadrons that contain only first generation quarks is a perfect tool to study such features of hadron production as strangest enhancement, recombination, and radial flow at intermediate PT range, and energy loss flavor depends at high PT range. The result will be compared to PFA8 and AMPT prediction to study strange meson production from different perspectives, like soft QCD, Lund model, and coalescence from quark-gluon plasma. Every knowledge is obtained only with systematic studies. This is why Phoenix studied different observables in a large variety of systems to reveal minimal conditions to form a QGP and understand its properties. In this talk, I will discuss about nuclear effects in small collision systems. About large collision systems will tell Daria Larionova. At the slide, you can see particles. The production will be discussed at this talk. Meson-containing strange quarks are shown at the left with quark-contain, decay modes, branching ratio, and mass. And non-strange hadron in the right with such properties. Let's start with the ratio of particles. New results and on charged hadron production, helium-gold collisions are presented. As one can see, neither Kn to pi ratio or proton to pi ratio don't show any centrality dependence. In heavy ion collisions, proton to pi ratio shows larger centrality dependence, while the ratio of two mesons such as Kn to pi ratios don't show centrality dependence. That was explained in the frame of recombination model of QGP hadronization. These effects will be discussed in Darius' talk. Actually, proton to pi ratio shows a hint of centrality dependence, but it's insignificant within uncertainties. Behavior of proton to pi ratio in helium gold collisions is rather close to such ratio in proton-proton collisions. In the slide, you can see comparison of ratio measured in small systems, including proton-proton collisions. Ratios in all small systems are close to each other. But proton to pi ratio in deuterium gold and helium gold collisions show a hint of centrality dependence. In central collisions, top right figure, they are a bit greater than ratio in proton-proton and proton-aluminum collisions. In peripheral collisions, ratio in all systems are in agreement, bottom right figure. Kn to pi ratio are in agreement in all centralities and in all systems, left figures. The nuclear modification factors for different hadrons is shown for most central and most peripheral helium gold collisions. In central collisions, proton yields are enhanced as in proton and deuterium gold collisions, while all other mesons independently of quark content lie on the same curve. The fact that proton RAB is larger than heavier phi meson RAB is more suited for recombination model because recombination gives the higher PT kick to baryons than to mesons and don't depend on hadron mass as radial flow does. The nuclear modification factors for different light hadrons charge pions and kns, pi 0, phi, k star, and antiproton are shown for most central and most peripheral proton-aluminum collisions. Charged particles RAB are presented with a field box of systematic uncertainties, and neutral particles are presented with empty systematic box. In central collisions, no baryon and stringent enhancement were observed. RAB of all hadron are in agreement within uncertainties. In order to understand the observed ordering RAB for phi mesons were compared to different model calculations. Experimental results are presented by red points with statistical and systematical uncertainties. The phi meson RAB were estimated following the procedure used for experimental data as a ratio of the phi meson production spectrum and proton aluminum, proton gold, deuterium gold, and helium gold collisions. Estimated with the PFA Angantyr to the same hadron production spectrum in proton-proton collisions, estimate with PFA8 at the same energy of 200 GeV, normalized by the same number of collisions values as in experiment. PFA results are presented by green curve. PFA8 underestimate phi-Rb in gold target collisions, while proton aluminum results are in nice agreement. The same can be said about default AMPT predictions, which are well described proton aluminum and fail to describe the large target. While string melting AMPT calculations, which include coalescence from QGP, overestimate proton aluminum collisions results, but fall on the same curve in proton, deuterium, and helium gold collisions. String melting AMPT results are presented by blue curve. Default AMPT results are presented by gray curve. This observation suggests that coalescence mechanism may start be important for phi production at system size between proton aluminum and proton gold collisions. Therefore, minimal condition to form a QGP might be in between these systems. Let me summarize. Minimal condition to form a QGP might lie in between proton aluminum and proton gold collisions, because we observe a hint of proton enhancement in proton, deuterium, helium gold collisions. From modeling results, we understand that coalescence became important in proton, deuterium, helium gold collisions, but probably the size and lifetime of QGP is not enough to see strangest enhancement. We are looking forward to obtain anisotropic harmonic and direct photons in proton aluminum collisions to reveal minimal conditions to form QGP. That's all I have for the day. Thank you for your attention.
Thank you, Vladislav. Any questions? I can't see question. Thank you, Vladislav, again. So let's move to our next speaker, Zandong San,
Thank you.
University of Debrecen.
All right, I'm going to share my screen.
Okay, you can see your slides. Please go ahead.
Okay, thanks everyone, and thanks for the organizers for giving me this opportunity to present my work. My name is Zhandong Sun from University of Debrecen, and today I'm to share some updates about the study of high PT direct photons in small systems at Phoenix. And this was introduced already, that this is the Phoenix detector layout, and the data used in this analysis was taken by the EM call, which is the most out layer of the side view. And this talk is structured as follows. I will start with the motivation, then the pi0 extraction and 2D method to correct it. The uncertainty is also studied. Then we move forward to decay photons. At last, I'm going to present the corrected pi0 and raw direct photons, and the summary at the end. First of all, so this is a plot of the published result and the preliminary result of the nuclear modification factor for pi0 in proton gold and deuterium gold collisions. And we observed something interesting. At high PT, we saw this large centrality dependence, and especially at high PT, we observed suppression in central events and enhancement in peripheral events, which is not as what we expected. So there must be some explanation behind the centrality dependence, either an artifact or some physics behind it. So one possibility is that the centrality could be mispinned in this analysis. This is a definition of nuclear modification factor, the yield in ion collision divided by the yield in proton-proton collision multiplied by the number of binary collisions according to global model. And we use, as you see in the middle plot, used to relate the number of charged particle and the number of binary collision to define our centrality experimentally. And this method works well in large systems, I mean in ion-ion collisions. And on the plot on the left-hand side, we can see the agreement between the N-core and N-charge. However, in smaller systems, since one type of the ion is very small, so this relation between the number of charged particle and number of binary collision might be different. Imagine when there is a high PT event happens in a small system, there wouldn't be sufficient background charged particle to help us to find out the centrality in our experiment. So, and direct photon could be the best solution for us to check our guess. And the reason is that so the photons is it has no color charge and it has non suppression from such heavy ion collisions. This has been observed in gold already. So ultimately, so we are going to make ratio between the direct photon and the pi0, and this ratio could come out with centrality dependence. If so, then we would say that the centrality dependence of the pi0 could be because of some physics effect. If it comes out without centrality dependence, then we highly support or claim that maybe we have mispinned the centrality, and this mispinning should affect direct photon as well. Okay, after knowing what to do, now to study photons, first we have to eliminate the decay photons as a background. And the major source of decay photon is pi0. Using the reconstructed invariant mass, we extracted pi0s. At low PT, the mixed event method is used. Then after subtraction of the mixed event, we had another second order polynomial fitting. While at high PT, due to the lack of statistics, we prefer to take average the average beam content of the area, the region outside the peak, and subtract it from the peak. Now we have the raw photons, raw pi0. It has to be corrected. At Phoenix, we first we have an acceptance correction. It includes the coverage of the rapidity that are hot towers or channels in the EM-core. And we also, in this analysis, we choose two photons in the same sector in our detector to pair up to reconstruct pi0s. This should also be corrected. And efficiency-wise, we have particle identification efficiency, and at high PT, especially in this decay, pi0 decay, we have merging effect and cluster breakup. We should also count them in. Another thing we should pay attention is that the reconstructed pi0 PT might be different from the true PT. And this migration is due mostly to the lower PT, and we can see it clearly from this simulation plot. So x-axis is the original PT, and the y-axis is the measured PT. So we see the migration, and inverting this so-called response matrix is very problematic due to the small and fluctuating off-diagonal elements. So instead of inverting the matrix, we have another solution. First, in simulation, we generate a pi0 spectrum, and it comes as a one-dimension matrix. Nn is the number of pi0 generated at Ptn, and put it into our detector and measure it in simulation. We will get a two-dimensional matrix, and the element xmn is the number of pi0, which is generated at Ptn but reconstructed at Ptm. Simply dividing each column by the corresponding parent PT, we will have a matrix of probability, and this is our 2D response matrix. Having this matrix, we gave a trial yield, and this yield is from our previous study in similar system. And make the multiplication, we have the measured yield. And this measured yield will be used to compare with our raw yield from data. If they don't agree, then this the ratio between them will be fed back to the trial yield, and we will measure it again. And the new measured yield will be compared again to the raw yield. We do this for several iterations, and eventually the measured yield will converge to our raw yield from the data. And at this moment, the final trial function would be the corrected yield. And these are some plots from this analysis. So on the left-hand side, this is the 2D response matrix. In the middle, we have on the above, we have the final trial pi0 spectrum. After the measurement, the measured pi0 is the magenta points, and they are behind the blue histogram, which is the raw pi0 from data, making the ratio. It has some fluctuation, but it seems good now. Okay, and the next step, we studied the propagation of, statistical uncertainty. On the left-hand side, this is the raw spectrum of pi0 from the data. And using this one, we randomize 3,000 sample spectra. And at each PT, we fill those values into histograms. They follow a Gaussian distribution, and all these 3,000 sample spectra will be measured by our 2D matrix or by our simulated detector. Corrected by our 2D matrix. And at each PT, we fill the values into the histograms and feed them with the Gaussian. The mean is going to be the final output of the corrected pi0, and the width will be the corrected statistical uncertainty. Wow, now we have corrected pi0, then let's switch to photons. We have inclusive photons in our detector, consists of decay photons and direct photons. since they have different properties, we couldn't correct them by one single matrix because kinematically the two gamma distribution should be flat, but actually we measured in detector is not always flat. We could see in this plot, x-axis is the PT of pi 0, y is the PT of the decay photons. At lower PT, it seems to be flat. However, at higher PT, we see at half of the pi 0 PT, it tends to be a valley. And this is because of the merging effect. When pi 0 decays to two similar gammas, they will fall into one cluster. But this kind of property doesn't show up in the case of direct photons, and the direct photons also don't exhibit wrong energy sharing of the neighbor clusters. Pi 0 is the major source of decay photons. We also have other decay sources like eta prime, omega. Using the IMT scaling calculation, we generated the cocktail ratio. One would wonder why this eta over pi 0 ratio is falling down, because I used a function from a recent study, which put it here. It used some machine learning techniques and find out a better fitting function for eta over pi 0. All right, so we have in this plot, we have corrected pi 0 with the statistical errors, uncertainties on it. It decays to pi 0 decay gamma, the magenta, and I scaled it by the cocktail ratio. As a result, we have the hadron decay gamma. This is the last slide. On left-hand side, what is shown is the invariant yield of pi 0 in p-gold collision in centrality classes. It has only the statistical uncertainty, and the systematic uncertainty is still under study. On the other side, this is the first spectrum of raw direct photons. The reason why I show only the high PT region is that there's a significant contamination by hadrons at lower energy in EM-Cal. So we are still working on it. And this is my summary. First, I started this talk by with the observation of our previous results, the central dependence in nuclear modification factor pi 0 in p-gold and d-gold. I introduced the 2D matrix method to correct for corrections. Statistical uncertainty was studied in the yield of pi 0, and we presented the invariant yield of pi 0 and raw direct photons. And to solve this puzzle of the central dependence, the ratio of direct photon over pi 0 would be our ultimate goal. Thanks a lot for your attention.
Thank you, Professor Sam. Any questions? Okay, I can see any questions. Then let's move to other speaker, Daria Larionova, St. Petersburg Polytech.
Hello, do you hear me?
Yes, we can hear you.
I'll share my screen. Does it go through?
No. Yes, thank you.
Okay. My name is Daria Larionova, and I am from Peter the Great, St. Petersburg Polytechnic University. And today I would like to present the report about Phoenix results on hadron production in heavy ion collisions. As was mentioned already in previous talks, one of the main ways to explore QGP is investigation of hadron production in heavy ion collision systems. And the most simple way to establish and study collective effects in heavy ion collisions is measurement of nuclear modification factors, which are quantitative characteristic of difference in hadron production in heavy ion collisions and proton-proton collisions. This slide shows different light hadron nuclear modification factors measured in copper-gold collisions, left picture, and uranium-uranium collisions in the right side of the slide. And here can be seen several patterns. First pattern is enhancement of values of proton array B over meson array B values. Particularly, proton array B values are greater than phi meson array B values, despite the fact that phi meson and proton masses are rather close. And so such behavior suggests a baryon versus meson dynamic as opposed to simple mass dependence. This effect is known as baryon puzzle and was firstly observed in gold-gold collisions in proton-to-pion ratios, which are shown in the figure in the right side of the slide. In proton-proton collisions, protons are produced 3 times less than pi mesons due to a larger mass and requirement of non-zero baryon number for the formation of a proton. However, in a large collision system, such as gold-gold collision system, the value of proton to pi meson ratio obtained by Phoenix experiment reaches the value of 0.8, as can be shown in the figure. Moreover, the value of proton to pi ratio in gold-gold collisions increases with the size of nuclear overlap region, which is usually characterized by the centrality and the number of nucleons participating in the interaction and part value. The larger in part value, the more central becomes the interaction of 2 nuclei. At the same time, Kn to pi ratio doesn't show any dependence on centrality and in part figure in the left side of the slide. And one of the ways to describe such behavior is to use recombination models of QGP hadronization. According to recombination model, hadrons are formed from quarks in QGP, which are close to each other in phase space. So they have close values of momentum and coordinate. The main parameters of recombination models are the temperature of QGP, quark chemical potential, and parameters responsible for the condition of closeness of quarks in phase space. So systematic study of different heavy ion collisions systems can provide experimental support to recombination model calculations and to study features of baryon and meson production versus collision geometry and system size. So that's all for baryon puzzle. And next pattern in the picture of light hadron array B in copper, gold, and uranium collisions is a coincidence of nuclear modification factors of mesons which are containing strange quarks, such mesons as K star, charged Kns, and phi mesons. They are presented in the figures with green colors. At the same time, values of nuclear modification factors of mesons without strange quarks, pi 0, charged pions, and eta mesons are also in agreement with the uncertainties, and they are presented with red, magenta, and blue colors. So, and RAB values of meson containing strange quarks are greater than RAB values of mesons without strange quark in content. And this effect is known as Strange's enhancement, and it was one of the signatures of QGP formation. In colliding nucleus, there are no strange quarks, but after formation in the quark-gluon plasma, as well as any hot object, heat transfer occurs. The energy is large enough to produce an excess of heavy strange quarks in gluon-gluon interactions. And moreover, if the QGP didn't exist, in the collision, the same energy would be converted into a non-equilibrium mixture containing strange quarks. And enhancement of strange particles production in heavy ion collision systems comparing to production in proton-proton collisions normalized on number of nucleon-nucleon collisions means that QGP was produced. And the last effect, which can be seen in these plots, is jet clinching. Jets interact strongly with the medium, and that leads to a marked reduction of their energy. So this leads to decreasing of hadrons in high PT region of heavy ion collisions comparing to proton-proton collisions. So in high PT region, RAB values are much smaller than unity for all flavors of hadrons. And this slide shows integrated phi meson and proton RAB as a function of number of participants. Both for protons and for phi mesons, integrated RAB are in agreement in different systems at the same and part values, despite the fact that uranium is collision of highly deformed nuclei, kappa gold is asymmetric system, and gold and kappa is symmetric collision systems. So scaling with n part might indicate that proton and phi meson production scales with average size of the nuclear overlap region and is independent of the details of its shape. And this slide presents theoretical predictions based on PFA8 model and IMPT string melting model. Angatir model in PFA8 is generalized the formalism for proton-proton collisions to an event generator for nuclear collisions and consequently considers only cold nuclear matter effects. IMPT is a multi-phase transport model which implements coalescence model and was constructed specifically for the study of relativistic heavy ion collisions. As one can see, string melting model IMPT, which is presented with blue color, well predicts nuclear modification factors of phi meson in kappa gold collisions, and so coalescence can be responsible for phi meson yields enhancement in central collisions. And at the same time, PFA8 underestimates experimental data and fails at central kappa gold collisions. Let me summarize the talk. Firstly, light hadron production seems to scale with the average size of the nuclear overlap region and don't depend on the details of its shape. Also, in heavy ion collisions, Strangen's enhancement and Brion puzzle are observed. And this can be, Strangen's enhancement can be explained in the frame of coalescence models, which was shown for phi meson by MPT calculations. And the last one, there is no flavor-dependent suppression at high PT in heavy ion collisions. That's all. Thank you for your attention.
Thank you, Daria, for this such clear talk. Any questions? Mikhail? Yes.
Thanks, Daria. But your final conclusion, no flavor dependent suppressed at high PT in heavy ion collision, it's very strong. I consider it's not right. It's
Might indicate.
Yeah. Thanks.
Okay, other questions, comments? If not, thanks again, Daria. And our next speaker is Alexander Lanyov.
Hello, can you hear me?
Yes.
Okay, I'll try to share my screen. Can you see it?
Yes, perfect.
Okay. Okay, so my talk is today electroweak measurements at CMS, and my name is Alexander Lanyov from Joint Institute for Nuclear Research. And today I'll present these electroweak measurements based on CMS public results, which can be seen here as usual. And I'll talk today about single ZW boson production, including the Driegan process according to this diagram, and show the total and differential cross sections and measurements of that invisible width. When I go to asymmetries, which include forward backward asymmetry, angular coefficients, and weak mixing angle. And finally, we'll come to multiple boson production. And according to these diagrams, for example, including also anomalous electroweak gauge couplings, and give my conclusions. So first, single ZW production, Driegan. Let's start with this slide, which shows the result of this physics analysis summary from CMS. It was based on the low PILAB data for TP inverse precobalance at 13 TeV, taken with dedicated LHC runs. And we use here single muon trigger PT greater than 20 GeV and pseudo rapidity less than 2.4. And you can see the results here at this spot, which shows cross-section times branching for different states, such as W and Z, and also W plus and W minus, as a function of center of mass energy from 7 to 13 TeV. And you can see that Z cross-sections and W cross-sections agree well between channels and with next in order PCD expectations. And here is breakdown on different channels. And there was a more recent paper which measured differential cross-sections on PT, Y, and phi angle. So here is an example for rapidity measurement. And you can see a comparison of different Monte Carlo generation programs, which show some small difference. Next, I show the slide for W boson decay branching, which is interesting from the point of view of lepton universality for weak interactions. And here it was measured branching ratio fractions of W bosons in three states: electron, muon, or tau lepton decays. And you can see the comparison with LEP. And the comparison with multicolor predictions. So agreement is good. And here this table shows the results which support the hypothesis of lepton universality for weak interactions. You can see different ratios, and you can see that precision of CMS is better than, for example, LEP, and it is a good agreement with the standard model. Also, correlations of the branch were measured with such two-dimensional plots, where different branches are shown in the horizontal and vertical axis. And I included in this slide also a new interesting result for lepton fiber universality, which was tested also in the recent paper published in Joint Journal of High Energy Physics for the first time at TeV scale. And what is plotted here is this ratio of cross sections of muon, dimuon, and dielectron channel as a function of the mass of the leptons. So the left plot is for barrel leptons, and the last plot, the right plot, is for the case where at least one lepton was in the end cap. A barrel is defined as should repeat less than 1.2, and you can see that the standard model prediction of unity is well reproduced for the first beans, and maybe not completely for last two beans. But here there is a large statistical error, so our conclusion is that no significant deviations from standard model is observed. So of course it is interesting how it would change with run 3, and these results were done for full run 2 data. Okay, next I continue with Driewian cross-section. Here for this paper we used 2.8 atmosphere turbines at 13 TeV. It was done at the beginning of the run, and now it is being analyzed for the whole run 2. And for this study we used mass range between 15 and 3000 GeV divided into 43 beans. And we used isolated single muon trigger with PT greater than 20 GeV, and the chematical cuts in offline analysis for PT for the leading muon is greater than 22 GeV, and for subleading greater than 10 GeV, and to repeat less than 2.4. So we can see the results here for differential cross-section over the mass, which is corrected here for the two full space. And there is comparison with the fuse results, which were done at next leading node PTD and next leading node electroweak. And agreement is rather good. So this paper also contained the measurement of fiducial cross sections with the different detector acceptance, and this analysis combined both dimuon and dielectron channels. So I continue with Driewian analysis. A little bit different type. So here it is done on mass dependence of transverse momentum. So what was measured is as a function of PT or phi star. It was measured the double differential cross section in the beams of dielectron masses from 50 to 1000 GeV. And this plot is for the last beam between 350 and 1000 GeV. So you can see the measurements compared with some Monte Carlo, and agreement is sometimes good and sometimes not very large, depending on the range of PT for which this or that Monte Carlo program was tuned. And additionally, similar measurements were performed in this paper requiring at least one jet in the final state. Okay, the next analysis is the measurement of multiple differentiable cross-section for production of Z boson and plus jets. And here we put PT as in different ranges of rapidity. And there's also comparison with Monte Carlo. So of course, leading order is not very well reproduced, but the next leading order and next leading order are reproduced rather well here. Okay, and next slide is for precision measurement of Z invisible widths. The result is shown here for CMS. So the invisible width is measured as 523 GeV, 23 MeV plus minus 16 MeV. And if you compare with this LEP combination, direct combination, so precision is similar to that. So this measurement is the first measurement of that invisible width at a Hadron Collider, and with a single most precise direct measurement in the world, which is competitive with the combined direct measurement from LEP. Now I come to next section of asymmetries and angular coefficients. So the first slide is a reminder for forward-backward asymmetry for Brilliant pairs. It is known that this quantity has a large value of 0.6 for large masses in the standard model. For example, here there is a port from CDF collaboration, 0.6, and there is a pole at the Z mass. And what is interesting in this measurement is that it can be a sensitive check of standard model, and also Langberg-Wick mixing angle can be also measured. Okay, and the result of CMS at 8 TeV is here, is presented here. So this is a definition of AFB, which is the ratio of difference F minus B and sum plus F plus B, where F and B are the number of events with positive and negative cosine theta star, where theta star is defined as the angle between mu minus and quark direction in CMS of dilepton. So there is some special feature of Hadron Collider that a quark direction is associated here in this analysis with dilepton boost direction. So, for example, therefore, with some dilution with small rapidities, but small dilution with large rapidities. And here is the results of CMS presented as a function of mass for different values of rapidity. Here y is smaller than 1, and for example here y is larger than 2.4. So you can see the good agreement to the standard model prediction shown with green boxes. So CMS did the first measurement at Hadron Collider, the plus and minus channel, and presented combination of dimelon and dielectron channel, and this can be used to measure the Weinberg angle also, which will be shown a little bit later. But there could be also some generalization of forward-backward asymmetry, because in principle the total differential cross-section over two angles contains not only A4 coefficient but also different coefficients A. So this coefficient governs the kinematics of the muons in Z2 mu decay. So here the definition of these angles, theta and phi, are the polar and azimuthal angles of negatively charged electron in the rest frame of the electron pair. So if we integrate all this expression over phi, we get just the previous expression that only with coefficient A4, which is just proportional to AB. And next slide, I show some example of these measurements. Probably the most interesting is the difference between parameters A0 and A2 here. And it is plotted here as a function of momentum, transverse momentum for different values of rapidity. So you can see that this quantity is not zero, and this means the violation of the so-called Lamtung relation, which this reflects the full transverse polarization of vector boson coupling to quarks. Okay, so in the paper it was provided similar plots for all A coefficient from A0 to A4, and this measurement provides comprehensive information about the Z boson production mechanisms compared to the PCD predictions. Next, I'll go to a couple of slides which describe the measurement of weak mixing angle with AFB. And this Weinberg angle, sinus squared theta effective, is defined as a coefficient in the relation for vector and axial vector couplings of Z boson in this way. And this also sorry?
2 minutes.
Okay, thank you. Okay, so then the next slide presents the results of CMS for Weinberg angle, and there is expected a further improvement in high luminosity RC by a factor of several times. Then I briefly go to the multiple bosons section. There were different papers for multiple boson production, which presents the test of standard model electrolytic theory and predictive PCD at TV scale. So the results present cross sections for different channels, which is agrees with Monte Carlo. This. And this gives also anomalous triple and quadric gauge couplings, which are important from the point of view of Chekhov electroweak sector of standard model, where there are self-couplings of these vector bosons. So, for example, this diagram is just absent in the standard model. So, if this exists, then it is something new. And this slide shows the limits on the anomalous triple and quadric gauge couplings. Here's the example triple couplings and some different measurements of CMS and datos and quadric couplings. So further experimental data for CMS and datos are compiled in this link. And finally, I'll just remind of the general panorama of standard model measurements, which were also presented on Sunday, yesterday, by CMS. And these are my conclusions. So CMS showed an excellent performance to detect different signals and produce many electroweak measurements at 7, 8, and 13 TV. It showed studies of different cross sections and many observables. It was done extracting parameters, testing various Monte Carlo models, leading to constrained PDFs. This is just an example where CMS measurement constrains the PDFs. And this is a precise measurements with Hadron Collider. So all measurements are so far in agreement with the theoretical predictions from the standard model. So no new physics is observed yet. So please stay tuned for any news with further analysis. And this is a reminder about the place where you can see the CMS publications for the standard model. So thank you for attention.
Thank you, Alexander. Any questions from outside? Okay, there are no questions. So let's move to our next speaker, Valery Pozdnyakov, Dubna Institute.
Hello. I
Hello?
start sharing.
Okay, you can share your screen.
Okay. Do you see slides?
Yes, you can see.
Okay, so I will present results. Actually, not only recent, some for some time on ultra-peripheral, so-called ultra-peripheral collisions study with ARES. So I will, at the beginning, I will explain what is ultra-peripheral collisions and what is the physics inside. I mean, what we can study and compare with the calculation. Most of the jobs were done for GPSI and Psi prime photo production, and for these couple of studies, the main question is gluon shadowing. I will explain in details on the next slide. And also, it's only one line, but within this line we have quite rich field to study ρ0 production from the point of view of black disk approach. So what we have for UPC? So UPC ultra-peripheral means that no hadron interactions between ions, and actually in this mode, for this study, LHC is used as a powerful source of quasi-real photons. So we have a photon-induced reactions. Actually, it's two items, two photons, but it's out of my presentation because it's just it's a pure QED process, and the main point here is just background for study of photonuclear reactions, where we have a photon which fluctuates into vector meson, and this vector meson scatters off target another ion either coherently on whole nucleus, and then vector meson, actually GPSI PT is around 30 MeV, or incoherently of nucleus, nucleons, and then we have 10 times more PT. It's important to understand that in this case, actually, we don't know which ion is a source of nucleus. So we have a bidirectional photon ambiguity. And another pretty thing is that since we have large ion charge, we have a huge photon fluxes, and within the same ion scattering, we can get, and you will see the results. We can get superposition of two processes. First one is a scattering of vector meson of ion, and second one we can get electromagnetic nuclear excitation due to additional photon exchange, and in this case, for excited nucleon, we will see neutrons detected in 0-degree calorimeters. Actually, we can also, this excitation can be followed by proton emission, but it's another story how to detect protons. So UPC studies are intended mainly for gluon shading in nuclei. And two-photon process, they are out of my presentation, and you can see the details of UPC reviews shown here. So for coherent GPSI photo production, it's quite simple. We have GPSI exchange by pomeron with another nuclei, and for this process, gamma nuclei, the cross-section is proportional to gluon density. And the main question, you see calculation of gluon density in lead ion for mass of GPSI, and you see how are different for each other. So the question is how to incorporate nuclear shading if there is, and it's our aim of our study. So we made a job with ALICE experiment, and actually for this study we need barrel detectors, actually inner tracking system, and TPC to detect and reconstruct particles in the barrel, and muon arm to reconstruct GPSI. So you can see what we use for what aim to detect, to trigger, and 0-degree calorimeter to detect neutrons coming from electromagnetic dissociation of nuclei. So you see that this, I would say, rich physics actually is contained in the quite simple topology. So it's real events. So it's for muons detected in a muon arm of the ALICE, and it's two particles detected in the barrel. So the main feature of UPC is quite simple. So exclusive events. We detect everything produced in UPC, and transverse momentum, balance of final state particles. I will illustrate this later on. So I will start from GPSI photo production in proton lead collisions, where we have no photon source uncertainty, since we know that mostly photons come from lead side. Gamma background is pretty small, and inelastic interactions suppressed by ZDC signal requirements. So we have quite large gamma proton invariant mass from 20 to 700, quite small X, and we made calculation of the cross-section as a function of gamma proton mass for different rapidities of GPSI. So you see here the results of ALICE together with the experiment on here, and LHCb experiment as well. So you see that actually power law behavior quite nice describe our results, and these calculations GMRT actually use the data for the fit. That's why if to have a look on the behavior, it's seen that this calculation is the best. So now I move to the coherent production of GPSI at forward rapidity in muon arm. So during round 2, we collected large luminosity, and also we got very nice condition for the triggering. When we we put to the detector so-called Alice diffractive detector. So we increased statistic of our sample by approximately 20 times. So you see, it's a PT distribution of GPSI. Logarithmic scale. So the main source is a subject of our interest, coherent GPSI. Also, we have a 2-photon production, and others are one order smaller. So 2 main sources. And on the mass fit, you see these 2-photon spectra, and also we have nicely seen GPSI and Psi prime. And you see the comparison with run 1. Here 30, 35, here 4,000, 5,000. So very nice statistics. And the conditions for coherent PT must be below 250 MeV, because as I already told that for coherent production we have we see small PT, actually 30 or 40 MeV, and it's a range of the rapidity and other things. And from this spectra, we calculate cross-section as a function of GPSI rapidity, and you see the comparison of our results with a couple of models. What we definitely see from this point, it's a impulse approximation with no nuclei effects, and it's definitely bad for the in the comparison with the data. So other calculations are quite close each other and to the data. So we cannot tell. We cannot conclude what is the level of gluon shadowing, but definitely we know 2 things. First one, gluon shadowing exists, because approximation without shadowing lost for the data description, and also strong gluon shadowing is also not nice for the data. So we conclude that actually we see moderate gluon shadowing in nuclei. Then we made the same study for GPSI and Psi prime photoproduction at mid rapidity in the barrel, in the small rapidity domain. Also, you see very nice GPSI in bath mode, muons and electrons, and we see not negligible sample of Psi prime in 2,4 prong. And we add this measurement to the what I show on previous slides. So it's a forward measurement of GPSI photoproduction, and it's a barrel. So we conclude that actually few models are in the game to describe the data, but it's interesting what's going on here. That's why I mentioned that we have some tension at semi rapidity and semi forward rapidity, but we have no data here. But in principle, neither this data nor this one are in disagreement with the calculations. So next study is a t-dependence, so square of momentum transfer between incoming and outgoing touch nuclei. And you see our results. So the cross-section as a function of t variable. And we compare this with a few, actually with 3 calculations. And what is it? Definitely, we found that Starlight Monte Carlo, which we used for the acceptance calculation, does not describe t-dependence. I mean the value. Maybe in shape it's not bad, but it's few times above the data. And a bad agreement comes from the model with the shading by leading to twist approximation from these two models, which are impact parameter dependent Baletsky-Kovchegev approach. So now I move to the
Sorry, 2 minutes.
yeah. So coherent Rho-zero photo production. So we detect a Rho-zero in barrel. We see some actually huge amount of the events, and we feed the data with Breit-Wigner, with Breit-Wigner and interference with direct pi plus pi minus production and some muon contamination to the sample. So I will try to go fast. So we made a measurement of Rho-zero photo production and compare with the same models as I mentioned, some models I mentioned above for GPSI. They were applied for Rho-zero through vector dominance model, etc., etc. You can see in the details what's going on with the models, but you see that our data are in between of Guzey, Krushin, Zhalov calculations in the lower limit of their calculation. It's the best description. What I told before, we have the DC, which can detect 1 neutron, 2 neutrons, 3 neutrons, and you see on a scatter plot of what we see in one arm of the DC. It's a 2-arm detector for bus side of our setup. So we have some sample with no neutrons, with at least 1 neutron on one side, and with neutrons on both sides. And we made a measurement of Rho-zero photo production cross-section for different scenario in the DC. So no neutrons, and we compare with the model with the same result for GKZ calculation. And we made a calculation for neutrons from on one side of the DC and neutrons on both sides. We conclude that we found agreement with the models based on a color dipole approach with a Gribov-Glauber shading. So we repeated this job for xenon UPC, and here statistic is quite small, and we got only 1 point, and compare with the same calculation from our authors, theoreticians. What we see that here we have some problems. I mean that our measurement is a bit lower of the calculation. So at this point I will omit because of the time. So in summary, we analyze GPSI and Rho-zero photo production, and we measured cross-section of GPSI photo production of proton and compare with another experiments. We measure coherent photo production of GPSI at forward and mid rapidity domain. We also measured Psi prime with a small but sizable statistics, and also we made for the first time we made a Rho-zero photo production cross-section in lead for different scenario with electromagnetic dissociation. And again, for the first time, we measured coherent Rho-zero photo production in xenon UPCs. That's all. Thank you very much.
Thank you, Valery, for such a nice talk. Any questions from outside? There's no questions.
Okay, so I stop sharing.
Okay. Our next speaker is Artem Isakov, Nuclear Physics Institute. Artem, you can share your screen.
Good afternoon. Do you see my slides now?
No, I cannot see.
Okay, and what about now?
Now it's okay.
Oh, great. So, good afternoon. My name is Artem Isakov, and I'm going to deliver you results of analysis of BJT production in PLED and PP collision systems at 5 tetraelectron volts measured with the ELIS detector. Ultra-relativistic collisions of heavy ions at the LHS creates high energy densities and temperatures, which leads the normal nuclear matter to transform to its deconfined phase, called coagulant plasma. And there are few significant signatures of the QGP formation: its collective flow and jet quenching. A large observed collective flow tells us that QGP acts like nearly perfect liquid, while jet quenching shows that QGP can slow down penetrating patrons. Effect of jet quenching can be estimated quantitatively with nuclear modification factor, which compares particle yield in heavy ion and PP collisions scaled by the number of binary nuclear collisions. And value of nuclear modification factor depends on different collision systems. In case of PLED, if it's not equal to unity, it means that we have some called nuclear matter effects. And in case of lead-lead collision system, if R is less than 1, it indicates the final state effects or medium energy loss. Big quark can be considered as ideal self-generated probes of QGP medium because they have a really long lifetime, so they will survive the whole evolution of the QGP, and they have a large mass, which means they can be created only in initial hard scattering, and their production rate can be calculated from Pedrov QCD. Another important point is the Detcon effect, which suppresses gluon radiation for massive quarks at a forward angle. On the left-hand side of the slide, you can see inclusive BJT spectrum measured by the CMS collaboration for starting from 50 to 400 GeV. Our goal is to extend this spectrum down to lower momenta, to the region where Detcon effect is more prominent. So it can be done with the ELIS detector, which you can see on this slide. It consists of central barrel and the muon arm. Detectors inside of central barrel are placed inside of half Tesla magnetic field. In our tracking, we are using time projection chamber and inner tracking system. For triggering, we are using V0 scintillator arrays, which are located at forward and backward pseudo rapidity. For our taking selection, we have charged tracks with pseudo rapidity constrained to plus minus 0.9 and full azimuthal range. So in ELIS, we have two independent methods for BJ tagging. First one is impact parameter method, which utilizes the distance of the closest approach of jet constituent to primary vertex. It's known that track originated from the primary vertex can be characterized with smaller distance to the closest approach in comparison with tracks which comes from the secondary vertex. So taking into account that, we calculate impact parameter significance as a ratio of two-dimensional impact parameter over uncertainty in this measurement. Then we sort this parameter for each track in descending order and select only mass displaced track. Second method is secondary vertex. In this method, we construct a secondary vertex or SV out of free jet constituents and select only the mass displaced one. On the next step, we consider discrimination variables. So first one is minimal significance of the SV displacement. This is just simply the distance between primary and secondary vertices divided by uncertainty in this measurement. Second variable is upper limit on the SV resolution, which is just a square root of the sum of distances of close approach for each prong to the SV. And on this slide, you can see our default SV cut. So upper limit is less than 0.03 centimeters and significance is more than 7. Both those methods, impact parameter and secondary vertex, provide the compatible results. So I will focus on the machinery only of one of them. So I will tell more precisely about secondary vertex. Okay, so the spectrum obtained with secondary vertex still need to be correct to account for purity and efficiency of BJ tagging. BJ tagging was estimated from E++ PFAIR detector level simulation as a ratio of the number of BJets without any the number of BJets that were reconstructed after SV cuts over the number of BJets without any constraint on a parameter of the SV. And one can see example of BJ tagging efficiency on the left panel of the slide for our default SV cut. We can see that contribution from the main background source from light flavor was suppressed by a factor of 100, while our target BJets has efficiency of 35%. Then next step is estimation of purity of BJet candidate. So it was done by hybrid method, which utilizes data-driven template fitting and POVIC simulation. So at first, the data-driven method described measured distribution of invariant mass of a secondary vertex as a linear combination of Monte Carlo templates. On the left figure, you can see example of such fit for PT being from 20 to 25 GV. Blue, green, and red histograms are invariant mass of SV for different BJet candidates, while black points is measured raw data. Magenta line is a result of the fit, and ratio of raw data to fit shown on the bottom panel, and it's compatible with the Unity. Unfortunately, results provided by data-driven method cannot be used for momenta larger than 30 GV because we have not enough statistics and we cannot apply fit to that region. And in order to obtain purity estimation for higher momentum, we used POVIC generator. So we have generated B and C jet particle level spectra with next to leading order POVIC generator, and then we folded those spectra with response matrix in order to obtain B and C jet spectra on the detector level. On the next step, we have calculated PT spectrum of light flavor jets on the detector level as a subtraction of raw PT spectrum of inclusive jets minus B and C jet spectra. And finally, purity of B jets can be estimated with a formula which you can see on the slide. As a result of this method, we have a set of different POVIC results, which differ by regularization and renormalization scale. So in order to select pleasurable POVEC settings, POVEC results were tested against the template fit results and by chi-square criteria. And one can see on this figure comparison between POVEC-based evaluation, which are shown by blue points, and red dots are data-driven evaluation. Both of spectra shown in a default SV cut. So finally, we have the differential production cross-section for B-jets measured at different collision systems for PP and PLET. Both results were compared with POVEC calculations, and they are showing agreement within systematic uncertainties. The next result is a measurement of B-jet fraction in PP collisions. It was again compared with POVEC prediction and showed compatible results. And our final result is a measurement of charged B-jet R-PLET, which was compared with POVEC plus PFAIR and with analogous measurements provided by the CMS collaboration for full jets. One can see that one cannot observe any strong cold nuclear matter effects in PLET collision systems within our current precision of the measurements. And our result is compatible with the CMS data. Okay, so let me summarize my talk. So results of differential production cross-section and B-jet fraction in PP collisions are compatible with the POVEC simulations. And within our current precision of charged B-jet R-PLET does not show to be affected by cold nuclear matter effects. And the Alice measurements of charged B-jet R-PLET is compatible with analogous CMS measurements for full jets. Thank you for your attention, and I will be glad to answer on your questions.
Thank you, Artem, for such a nice talk. Any questions from outside? Mikhail, yes?
Thanks, Artem. It's very interesting. You mentioned about B-tagging inclusive cross-section in PP. Could you compare or could you send some words about the comparison with the usual PCD jets, U and D? Because this B-tagging, there's a specific flavor dependence of the jet production.
I'm sorry, did I understand you correctly that you are asking to make a comparison with different
No, comparison, because Alice measured the inclusive jet without tagging. That is why you compare the B-tagging jet and untagging jet.
Okay. No, I mean, I'm comparing in both cases, this is charged B-jets. It's not inclusive spectra. Or did I understand you correctly?
No, but maybe yeah. Okay.
So this is both a charged B-jet.
Okay. But it's interesting the shape of the jet. It's independent of the charge because there is some maybe some specific of jet production.
Oh.
With big quarks or U or D quark or C quarks.
I mean, actually, I do not have comparison between charged and full jet production cross-section. So we did only comparison of R-PLET, and since this is just a ratio or in different collision systems, it will not take into account shape. It will just show how it's different it is in a different collision systems. So we cannot say how our spectra just shape how it's different in case of full and charged jets, because we did not make such a comparison.
Thank you.
Yeah, thank you. for a question.
Any questions? If not, thank you, Artem, again.
Thank you very much.
And we come to the conclusion. I would like to thank to all speakers and participants, and especially to organized committee and Alexander Studenikin. So maybe anybody want to say something?
Yeah, well, okay, thank you, Dmitry. Well, I would like to thank at the end of this, as we term it, Physics at Colliders session for very intense discussions. And I should say that this is the most important, in the sense that it's the most long and the most intense from the point of view discussions during the talks, and from the point of view of number of the presentations of today's parallel sessions. And I would like to warmly thank all the speakers, especially those who were speaking in the second part of this quite a long session. And of course, many thanks to Dmitry for his very nice chairmanship on this not easy session. Well, thank you very much, and I am sure that all of you will join us and join the Lomonosov conference just from the very morning tomorrow. That will be the one but last day of the conference, so we have to continue our work just to finish it with the big success. Okay, I would like to invite everybody for tomorrow. Yeah, thank you once again. Okay, thank you. Bye-bye. Okay.
Dmitry, good luck with our studies. Bye-bye.
Bye.